Okay, so at this point, we've taken our initial differential equation, which was eta squared minus k. No. Okay, so at this point, we've taken our initial differential equation, which we wrote down earlier. It was second derivative of this wave function is equal to eta squared minus k times the wave function. Right, and we've reduced this problem into solving this one up here. So, and let's recall really quickly how psi is actually related to h. Psi is equal to, psi of eta is equal to h of eta times e to the power of negative eta squared divided by 2. And the way we're going to go about solving this differential equation up here is we're going to expand h as a power series in eta, and then all of this with the intention of obtaining a recursion relation on the coefficients, and then determining what those coefficients have to be. So let's expand this as a power series, and the reason we can do this is because we know h is going to be reasonably well behaved, and for any well-behaved function you can expand it as a power series. So h of eta is going to be equal to some coefficient plus a sub 1 times eta plus a sub 2 times eta squared, and so on to infinity. So this is an infinite sum. Right, and let's also find the first and second derivatives of h. So we'll have our first derivative, and I'm just going to differentiate this here. This is equal to another infinite sum from j sub 0, or j is equal to 0, j times a sub j times eta to the power of j minus 1. And our second derivative is going to also look similar, which is equal to, now I just differentiate this. Right, but notice here, the first two terms are going to be 0. So we can actually just substitute j plus 2 for j, and then take that infinite sum starting from 0. So and these two things are entirely equivalent. And there's a reason we're not doing that here. And the reason is that when we plug this back in, this is going to receive another eta term to it. So this j minus 1 power is going to become to the power of j. So it's going to make it easier for us when we combine like terms. So let's plug this back in. We know this whole thing has to be set equal to 0. So we have this infinite series from j is equal to 0 to infinity. So let's start with our second derivative term, which is here. We have j plus 2, and these are all in the same summation from j is equal to 0 to infinity, so we don't have to separate the different sums. We can put them all into the same sum. Right, and then we have minus 2 eta times the first derivative with respect to eta. Right, but this eta is going to hit this one over here, and we just have to change the power. Okay, so, and then plus k minus 1 times h. But h is a sub j times eta to the power of j. And all of this equal to 0. And it follows from the uniqueness of power series expansions that if this power series is going to equate to 0, then every term has to vanish. So every power of j or eta has to vanish. And that's good for us because we can just get rid of this sum here and just say that this needs to be equal to 0. Okay, so immediately we can get rid of eta. And now we just solve for a sub j plus 2 in terms of a sub j. And this is going to give us a recursion relation for our coefficients. Okay, so that's pretty good. We've done what we set out to do. The only problem is this recursion relation jumps by 2 every time. So we can only choose to either get the odd coefficients or the even coefficients. But we can just do both. So if we have a sub 1 or a sub 0, we can get a sub 2, a sub 4, and so on. Or if we were given a sub 1, we could get a sub 3, a sub 5, and all the odd coefficients. But of course, h is going to include both of these, so h of eta is going to include h odd, and this is just all the odd coefficients and the odd powers, plus h even. Okay. So now let's examine this recursion a little more and see how a sub j is going to grow as j grows. So approximately a sub j plus 2 is equal to 2j over j squared times a sub j, and of course this just cancels, right? But this is then going to be equal to 2 over j times 2 over j minus 2 times a sub j minus 2. And you can see this pattern is going to keep going. And it's going to give us approximately, for a sub j when j is large, approximately some constant over j over 2 factorial. So now if we include this for our coefficients in h, we're going to have some sum, and we can be extremely approximate here because all we're trying to show now is that we're going to get some sort of exponential behavior, right? And then these are going to have for each coefficient, it's attached to a power. So just for example, h odd of eta is all the odd powers. And so on. And then h of the even ones are likewise just the even powers. So that's where this comes from. Okay, so now we're looking at an infinite sum with each of these powers of eta, and there's going to be some factor here that's 1 over j over 2 factorial, and it looks pretty similar to the expansion for the exponential, which is just one over j factorial times x to the power of j. Right, it's pretty close, but instead of j factorial, we have j over 2 factorial. But if you think about it, it doesn't really matter with what we're trying to prove. In fact, we can replace j by 2j, because if j is a power in the coefficient, or a power in the expansion, then 2j will be 2. So the sum has to include all the 2j's. And if we just make that substitution, we know at the very least our sum is going to include these terms. right? So we know that h of eta at the very least is going to go like the exponential of eta squared. But this is actually a bit of a problem because if you remember, we defined our wave function to be h of eta and then times this other exponential, which is negative eta squared over 2. But if h of eta goes like this, then our wave function, which is what we're trying to solve for, is going to go like eta squared over 2. And this is obviously a problem because this sort of solution won't be normalizable. So given this exponential behavior, we can say that there needs to occur some highest coefficient such that the recursion breaks. So the recursion has to terminate at some point. And what that means is there should be some value n, some j, we'll call it n, such that n plus 2 is going to be equal to 0. Because we have our formula for a sub j plus 2. And I'll just write it again real quick. Right, and if we require that a sub n plus 2 is equal to 0, then we have that 2n plus 1 minus k must evaluate to 0, and k is equal to 2n plus 1. Okay, so now if you remember from the algebraic solution, k, what do we have k? K is equal to 2 times the energy over h bar omega, which is equal to 2n plus 1. So if we solve for the energy, we have h bar omega over 2, or just h bar omega, times n plus 1/2, which is precisely our energy levels for the harmonic oscillator. And we've recovered the same exact solution from an entirely different method. So that's pretty cool. So we know we're going to have some highest coefficient, a sub n plus 2, or the highest one will be a sub n, because a sub n plus 2 is going to be equal to 0. And n also corresponds to our energy levels. So we can find out the allowed values of k in terms of n, which is just 2n plus 1. And additionally, we should notice that if we're going to set it so that this breaks off the recursion relation, it'll only either work for the odd or the even series, depending on which one we choose, given that the recursion relation jumps by 2. So when we're working with even energy levels, we're just going to set a sub 1 equal to 0 so that these odd coefficients don't grow and cause h of eta to get huge. And likewise, when we're working with odd coefficients, we set a sub 0 equal to 0. And now we can go ahead and start computing h of eta for different n values, so for different energy levels. But firstly, let's substitute for k its allowed values, which is 2n plus 1. So we have, for our new relation, minus 2n minus 1. And the denominator is the same. So a sub j plus 2 is equal to 2j minus n over j plus 1 times j plus 2 times a sub j. Now, looking at the ground state, we're just going to have one term, h of eta is going to be equal to a sub 0, because if we try to get a sub 2, this is when j is equal to 0. We're just going to have 2 times 0 minus 0 in the numerator, and this is going to vanish. And so now let's look at the first excited state, and we'll have, I'm going to start labeling these with some subscripts. So we're going to set a sub 0 equal to 0 because we're working with the odd coefficients. And then we want to get a sub 3 in terms of a sub 1. So a sub 3 is going to be 2 times, if we plug in 1 for j, 1 minus the energy level, which is 1, and of course this numerator vanishes too. So we have, for our second polynomial, just the first coefficient and the first power of eta. And now for the second excited state, we're going to set a sub 1 equal to 0. And then let's see what a sub 2 is going to be. It's going to be 2 times negative, or 0 minus the energy level, which is 2, over 1 times 2 times a sub 0, which is just going to be negative 2 a sub 0. So for our second energy level, we have negative 2 a sub 0 eta squared plus a sub 0, which is this 0th coefficient, times 1 minus 2 times eta squared. Okay, and then we can keep going and do n is equal to 3, n is equal to 4, and so on. But you get the gist of it now. We just use this recursion relation, which is just entirely equivalent to the solution. And so just like that, we've obtained our wave functions, because we know our wave function is equal to h of eta times e to the negative eta squared over 2. So our ground state then is up to some normalization constant, e to the power of negative eta squared over 2. And our first state is just eta a sub 1 eta times e to the power of negative eta squared over 2. And then our second excited state, which is the last one we'll compute for now, is a sub 0 1 minus 2 eta squared times e to the negative eta squared over 2. So it's clear now that given some value of n, we can get some polynomial in terms of eta using our recurrence relation above. And these aren't so random. They're actually a very common type of polynomial, and they're heavily studied and researched. They're called the Hermite polynomials. So now we'll just denote them with the capital H and eta here. And these happen to correspond to different stationary states in the solution for the harmonic oscillator. So just like that, now we've obtained the different, or we got our energy levels, which is h bar omega times n plus 1/2. But we've also gotten our wave functions, or stationary states, which is just going to be this polynomial that we've been computing up until now. Like this was the second, this was the first, this was the 0th, and then times this exponential. And there will be some normalization that we haven't computed, but you can compute that relatively easily. Just like that, we've gotten our solution from an entirely different method, and now just plugging in our value for eta, which was mass times omega over h times x. See, this would have been in terms of eta, and this one in terms of x. We have this Hermite polynomial times, or with respect to this value, and then this exponential, which should now look familiar. This is the solution we got in the algebraic method as well. So it's the exact same solution, and yeah. So thank you. In the next video, we'll be moving on to the free particle, which is not so hard to solve, but a trickier concept for sure. So thank you.